A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to another video, and today a problem suggested by a subscriber: the square root of I minus the square root of I minus the square root of I, and so on. It's another nested radical, a rested radical here on this channel. Have done a lot of those, and I'm fairly certain that I can solve this one, hence it's an improvised session, so I hope I'm not going to fuck anything up. Other than that, before we get started, first things first, this video has been sponsored by the wonderful people over on Print. More information at the end of the video. And since this has been suggested by a subscriber, I'm just going to use the axiom of this is probably solvable. So I guess this right here converges. If it doesn't, then that's a dick move. Sad thing with nested radicals is that you can find a nested radical convergence solver over on the internet to see if it actually converges. So I'm just going to think that it's converging. So the thing you normally do on nested radicals is that you just say this right here is equal to some x, because we want to solve for this very x. Now the cool thing about nested radicals is if everything is repeating, then you might notice that since this right here is infinitely often repeating and nested in and of itself, that this part over here is the same as our original x. So by declaring that this part right here is equal to x, we are going to end up with the following relationship, namely that x is equal to itself, kind of. It's recursively defined as the square root of I minus x. And this right here immensely simplifies our problem in a normal case. And now we can just solve for x. This is fairly straightforward. We can square both sides. We are going to get that x squared is equal to I minus x. And now we can solve for x. We can add x on both sides and subtract the imaginary unit I on both sides, giving us x squared minus I. Now I'm going to put the x here, so plus x minus I is equal to 0. And now using the quadratic formula, our coefficients are respectively 1 and negative I. So what we are going to get is that x1 and 2 are hence negative 1/2 plus or minus the square root of. We are going to get a quarter and then plus I. And I'm going to bring this into the typical American form of, I mean, we can already call it quits here, but there would be a very short video. But people's attention spans are fucked anyways by now. But other than that, if we bring it into the typical American form for the quadratic formula, this right here turns into negative 1. So we get over 2 plus or minus the square root of, then we get 1 plus 4i. I mean, this is the only interesting part here. I guess we still have a complex square root, which kind of leads us back to the original equation, because kind of we wanted to rationalize this in some kind of way. Now, typically, the square roots of complex numbers end up with complex numbers once again in a normal case. So what we could do to make this a bit more interesting is to evaluate the actual value of the square root right here. So I might as well do this. But other than that, this right here is already our solution. I mean, it's a bit unsatisfying, I suppose, but we can go a bit further. Let us take a look at 1 plus 4i, but the square root of that. So the square root of 1 plus 4i. This right here is going to yield a complex number in some kind of way. So of the form a plus ib. So we can solve this by, once again, it's the same procedure as here. We are going to, well, that's a substitution once again, just like we did before. We are going to square both sides, giving us that 1 plus 4i is hence equal to a plus ib, but the whole thing squared. And by squaring this, we are going to get a binomial formula just with I as a coefficient, meaning I times b squared is going to turn into negative b squared overall. So this is a squared minus b squared plus 2iab. And now we can simply compare coefficients. And this right here is already the standard form for doing something like this. You are going to notice that the real part of this complex number 1 is equal to the real part of this complex number. Namely, this is a squared minus b squared. we are going to get a system of equations. This is nothing new. I have done this several times here on this channel. So a squared minus b squared is hence equal to 1. And over here for the imaginary part, we get that the imaginary part must be equal to 4. But now by ignoring I, this must be equal to 2 times A times B. 2AB is equal to 4. And that's the system of equations that we can now solve. The first one sucks a bit. There would be the difference of 2 squares. But this wouldn't help. Let us solve the second equation for, I don't know, B, for example. So hence, by reformulating this, we are going to get the system of equations that a squared minus b squared is equal to 1. And b is hence equal to 4 over 2a, which is the same as 4 and 2, so 2 over a. And now we can plug the value for b into here, giving us overall that a squared minus b squared, so this is 4 over a squared, is equal to 1. And this right here is a 4th degree polynomial. But the cool thing about this is that it's a biquadratic equation. At least that's what's called in German, biquadratische Gleichung. I'm going to show you how you solve something like this. So this right here is equal to, under the condition that the real part is not equal to 0. It's not. Hopefully, we are going to get that a to the 4th power minus 4 is equal to a squared. Now subtracting a squared on both sides, we are going to get that a to the 4th power minus a squared minus 4 is equal to 0. This right here is a biquadratic equation, which is actually very easy to solve because all of those unknowns right here have even powers. So we can introduce yet another substitution, and we are going to say that let t be equal to a squared. So you're going to notice that a to the 4th power is the same as a squared squared, so that's the same as t squared. Then we are going to get minus t, and here, this right here, we have 4 times t to the 0th power, but t to the 0th power is the same as a squared to the 0th power. So just negative 4 is equal to 0, and that's just a quadratic equation that can now be solved once again. So we are going to get that t, 1 and 2 is equal to 1/2 plus or minus the square root of 1/4 plus 4. 16 over 4, so 17 over 4, turning this into 1 plus or minus the square root of 17 over 2. And remember, t is nothing other than a squared. So what we can now do is we can take the square root of this whole thing, plus or minus the square root, giving us overall that a is equal to the square root of 1 plus or minus square root of 17 over 2. And this right here is the real part of our complex number, where our complex number was just 1 plus 4i by the square root of that. We know what b is. B is equal to 1 over 2a. So b is hence equal to not 1 over 2a, 2 over a. 2 divided by all of this shtick right here. So the square root of 1 plus or minus the square root of 17 divided by 2. So we found out what our complex number's value is, meaning we are going to get a solution, and regularly you have plus or minus here, but if I'm not mistaken, the plus or minus really doesn't matter for the solution overall, because all of those branches and all of those combinations lead to the very same value for the complex number. But I'm not certain about this right now, to be very honest. So overall, what we are going to get, the solution to our rested radical x1 and 2 is the same as negative 1/2, and then we are going to get plus or minus the square root of what we had here, this right here, but with a 1/2, so plus or minus 1/2 times the square root of 1 plus 4i, but the square root of 1 plus 4i is the same as a plus ib, where a is this part plus I times this part, so 1/2 times plus or minus the square root of 1 plus or minus square root of 17. Oh Lord. Over 2 plus or minus I times 2 over the square root 1 plus or minus square root of 17 over 2. And well, that's about it, I suppose. And this very complex problem turned into an even more complex solution. That's a real bummer. I think the aforementioned solution, the first one, looked a bit better than this abomination, but what can you do? That's mathematics and complex numbers for you. And if you did enjoy what you have seen today, then you might certainly also enjoy the contents of today's sponsor Brain, who are kind enough to sponsor yet another video here on this channel. Now, that was quite a cool problem. I hope I didn't mess anything up. But this solution right here is kind of not satisfying, I think, because it's just using the real and imaginary part of complex numbers, which is one very nice representation that you can use, an algebraic one. But there's an even nicer representation on the unit circle, using the sine and cosine form of complex numbers. And this is also something that you could use here. And the cool thing about the unit circle is that you can graphically interpret complex numbers by using this special form. And this is where Brain comes in extremely clutch. With their huge variety of online courses in all topics STEM, be it the mathematics that we did today, physics, computer sciences, chemistry, Brain provides you with some of the best online learning content that you can find out there on the World Wide Web. And it's a seriously unique approach to learning something new on a daily basis, be it at home, on your PC, or on the go on your mobile phone. They use graphics and visualizations to make things like complex numbers or maybe redox reactions in chemistry way more easy to grasp. You can use a graphic and play around with certain parameters to vary, for example, the angle in the unit circle, or maybe angles inside of a triangle, or how the focus of the parabola changes by varying the stretching parameter, and so on and so forth. Brain is just an extremely crazy good source to learn something new on the go or at home on a daily basis. And I can just not emphasize enough how seriously amazing their course concept is and how easy it is to get started into a new topic in STEM with their online course concept. And don't take my word for it, try it out for yourself by using my link here at the top of the description, brain.org/lembelmaths. With it, you are going to get a 30-day free trial of amazing awesomeness. Try the whole landscape of Brain for completely free. And if this feels like this could turn into a long-term relationship between you and their services, then definitely make sure to use the link entirely to get 20% off an annual premium subscription, which is an amazing deal. There's so much content readily available, and they are adding so much content on a regular basis. It's just an absolute bliss. I just love the services and what they provide to a huge community of STEM interested people, and you should join their family too. And I hope you did enjoy what you have seen today. I certainly did like this problem very much. And up until the next video, I wish you guys a flammable day. See ya.